Assalamualaikum and good evening. So we continue uh, our lesson. We have come to current to voltage converter in the uh, last lecture before the semester break. Okay, and we have discussed the important features of analog digital converter. So the analog digital converter can also be used as a digital to analog converters that there are basically two devices that convert either from voltage analog voltage to digital or digital input into analog. Okay, so the basically this equation, as you can see, this equation is basically show you the equation output analog output is equal to the reference input of the ADC multiply with the digital input in binary. Okay. So the analog output, so we are talking about digital to analog, okay, can be estimated by this equation. Okay. So VR is the reference voltage given to the digital to analog converter, and B in this equation, B1 is the bit value, in the digital information, okay, or digital signal, okay, and from left to right in numbering position, okay, not according to the least significant bit, meaning that if B1 is the bit value, let's say this is the information, okay, okay, so this is according to this equation, okay, this is bit at the first position, okay. This is second bit value at the bit value at the second position, and so on, and this is the end. Okay, can depending on the bit number. So in this case, this is the bit value at the 8th position. Okay. Each bit value multiply with the 2 to the power of the position, okay, value. For example, this bit position is at 1, so 2 to the power of -1 plus with B2 multiply with 2 to the power of -2 and so on. Okay, so using this equation, we can estimate the analog output. Okay. Okay. So if we have 4-bit words, okay, so the maximum voltage output or analog output value, okay, at any given any time, value of the analog signal can be given by this, okay, estimation upon where we assume that the 4-bit word, okay, maximum value 111 1. Okay, so and then we get 0.9375 multiplied with the reference voltage. So reference voltage. Okay, usually it can be in the range of negative 15 to positive 15, depending on the type of the digital to analog converter. Okay, or we can use this equation in the analog output equal to n is the uh, decimal value of the digital input. Okay, decimal value in base 10. Okay, decimal value in of the digital input divided by 2 to the power n. N is the number of bit. Okay, total number of bit. Okay, total number of bit of the digital analog converter multiplied with the reference. So we can also use this information. Okay, for an example here, so we have a DAC. Okay, so sorry. So this is our DAC. Okay, we have digital inputs. So in this case, it has 8 bits. Okay, 1 to 8 bits, and the okay, okay, uh, okay. And the reference okay, we are basically equal to 5 volts. So what is the value of V out? Okay, when the input is 10100011. Okay, so we convert that to decimal value. Okay, base 10. Use your calculator. So we get 167 decimal. Okay, divide by 2 to the power of 8, the total number of bit, okay, bit places. So multiply with the reference. Okay, so in this case we get 3.2617. Okay, note that this output, okay, will always be less than 5 volts, not more than 5 volts. Okay. Okay, so let's see another example. Okay, in this example, what is the output voltage of 10 bits? Okay, 10 bits with the 10 volt reference. Okay, and also what is the digital input needed to get an analog uh, 5.625. Okay, so you can use the equation V out to n over 2 to the power of n multiply VR. Okay, or you can use the uh, uh, other methods. Okay, but using this equation, okay, you have to check the calculator how many bit places it can convert. Okay, your calculator, okay, how many bit places, how maximum, what's the maximum bit input digital place that can uh, convert. Okay, if that is not okay, possible, you can use the origin or the first equation. Okay, so here, okay, here, as you can see, okay, So 2 to the power in the first place, the bit place is equivalent to 0. So that, that so the multiplication of 2 to the power of 1 multiply 0 will get 0. Okay. Second also the same. Okay, this is the third. Okay, the third. So here E3, okay, multiply with 2 to the power of negative 3, and basically the, okay, because the value is 1, so you get this term plus, okay, this is 0. Okay, this is the fifth place, sixth place, okay, eighth place, and 10th place. Okay, so you get this. Okay, then you find the equivalent value, multiply with the reference. Okay. Uh, the second question, how what is the digital output? Okay, digital output. Okay, you can see quickly or directly use this equation. This equation. Okay, so given the out. Okay, and so we don't know the digital value. Okay, but we know the n, or the total number of bit places, is 10. As 10 as given right here, n is 10. Okay. And the reference is 10 volts. Okay. Okay, 10 volts. So we find n in decimal is 576. Okay, 576. And then in binary, we do the conversion. In binary, we get 1001 000 000. Okay, that is 2 of 2 or binary. Okay, so when all input are high, what is the reference voltage of 4-bit DAC? Okay, so you can use V out equivalent to VR multiply with n divided by 2 to the power of small n. Okay, so in this case is 4-bit, so all input are high, meaning that n in binary is equivalent to n 1 1 1. Okay, which is equivalent to what, 15. Okay, is it 15 or 16? Okay, 1 1. Okay, okay, so 1 1 1 1. Okay, so basically 2 to the power of 1, 2 to the power of 1 plus 2 to the power of 2, sorry, 0 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2 plus 2 to the power of 3. Basically 8 plus 4 plus 2 plus 1. Okay, isn't it? You get 15. Okay, in decimal, so 50 to the power. Okay, so 2 to the power of n is to 4 bit places. Okay, this is equivalent to what, 16. Okay, 16. Okay. So let's say your output voltage or the analog, the analog is input, 8, okay, therefore 8, V out, so 8, so V out is equivalent to V out. Okay, so 8 equivalent to VR multiplied with 15 divided by 60. So your VR is basically slightly higher than 8 multiplied with 16 over 50. So you get how much? So your V reference is 8.53 volts. Okay? So observe that the V reference, it will always be higher than the output. Okay, so, so in any cases, the output, panel output, will never be bigger than the reference input. Okay, this formula, okay, explain the resolution. The resolution is basically the smallest change the digital to analog converter can produce or or measure. Okay, if analog to digital, the resolution is the smallest conversion. Okay, it can produce, but analog digital to analog is the smallest output it can produce. Okay, so the formula here is data out equivalent to the reference multiplied by to the power of negative n. So in this case, the resolution is not based on the minimum and maximum limit. Yeah, not based on the minimum and maximum input. Okay, input limit. Okay, so this in this formula we can estimate. Sorry, okay, so this equation can be used. Okay, so for example, 5-bit digital converter with 10 volt reference we provide. Okay, sorry. Okay, so the smallest change it can provide is 0.3125. Okay, let's increase the bit. Okay, so let's say this is when we have 5 bit. Okay, 5 bit. So let's double the bit the bit of the digital analog converter. Let's say 10 bit. Okay, and then we fix the reference. So delta out, it will be 10 to the power of 2 over 10. So that basically will be much smaller. Is it too big? My calculator cannot calculate. Yeah. What is the value? But anyway, okay, in this case, okay, we should expect a smaller number of the delta out. Okay, the out, and we use P1024. So 10 divided by 1024, so we should get it, 0.00097 volt, okay, or 9.7 millivolt. Okay, 9.7. Okay. This one is around 312.5 millivolt. Okay, for higher bit means that the resolution is much smaller. So in this regard, the quality of the output signal, it will be much better if we have higher bit. Okay, let's you can, if this digital to analog is used with 5 bit. Okay, if perhaps let's say you have a analog sine wave, so for this kind or this bit number, the output, okay, you we have much uh, obvious steps. Okay, if we 5 bit is 5 bits, but for 10 bits perhaps, okay, the steps will be not much. Okay, if you zoom, you can see the step or the step on the output. Okay, okay. But if you have a smaller resolution, the output uh, will represent the input or the analog input much better. Okay, so that's the difference of resolution value uh, of digital to analog in terms of the value, So meaning to say, okay, if the digital analog converter have a smaller resolution value, so the quality of the output, okay, should be better. Okay, should be better. Okay, so let's look at this example. Okay, this is an example. We read the statement here. A control valve have a linear variation of opening as input varies from 0 to 10 volt. Okay, 0 to 10 volt. A microcomputer output 8-bit word, okay, to control the valve opening using 8-bit digital to analog converter to generate the valve voltage. Okay, basically, okay, what is happening? Okay, the key point here, we have a control valve. Control valve. Let's see. Okay, we have a pipeline. Okay, okay with liquid flow. Liquid flow. it can be anything. Okay, let's say your pipeline in your household. Okay, so you want to control. Okay, you want to control, okay, the flow. Okay, so you want to by controlling the flow. Okay, so you can control the amount of water transfer. Okay, uh, transfer at a certain amount of time. Okay, uh, if you, let's say, want to one more water to be used at a certain time, you, okay, open the valve larger, the opening of the large larger. But if you want to, let's say, you want to limit the flow, then you close. Okay, let's say this is a symbol of valve. Okay, valve, basically your water tap. Okay, what you have in your house is a kind of valve. Okay, your faucet is basically a kind of valve which you use your hand. Okay, you turn the knob of the faucet, or you the dial, okay, by clockwise or counterclockwise, okay, to open the valve. Okay, basically. But in this case, okay, in this case, we have automate the valve. Okay, the valve is connected. Okay, the connected to a motor. Okay, that will automatically turn, okay, the the screw, or the screw that close and open the valve. Okay, and then that motor is, we assume that it is drive by analog input. Okay, the motor, the input of the valve. Okay, motor okay, the control input. So it is an analog device. Okay, so this part is analog. Okay, this is analog. This part is analog. Okay, so the input range for the motor is 0 to 10 volt. 0 to 10 volt. Okay, and basically, uh, you have a microcomputer. Okay, your microcomputer may, okay, receive a, okay, input, let's say, from a variable register. Okay, to the thing, or maybe it connected to other system which receive information from remote server, for example. Okay, so your micro computer, okay, but microcontroller process information in digital. Okay, when it has an output, the analog output, but it is not suggested to, it is not preferable to use the analog output to control uh, what we call as the actuator. Okay, actuator, because they, you tend to, okay, okay, consume large current, and then microcontroller cannot support. So we need the digital to analog converter. So the input to the digital analog converter in this case, okay, 8 bit, okay, 8 bit, okay, okay, and this and then here it give the information that what is the reference, okay, VR that required to, okay, make the valve open full. Okay, so we can say valve, the valve opening, we can, let's put it as percentage. Okay, and then would be the analog input. Okay, the analog input from 0 to 10. Okay, so we assume that it should be linear. Assume that this is linear. Okay, when 10 volt, the opening is 100%. Okay, we assume 10 volt. Okay, here 10 volt, 100% valve open, and then liquid flow the maximum. Okay, and as the uh, input analog input to the valve is decreasing, so the valve opening is decreasing. Okay. So what is the VR required? Okay. So we can directly use the equation V out, okay, equivalent to VR multiplied with Vn, okay, over 2 to the power of small n. N is the decimal value of the digital input. So digital input is 8-bit. Okay, so if you work out here, the maximum is 10 AVR here. Here is 1111 1111. Okay, because when the output is at 10, so microcontroller should send a maximum value of bit information. Okay, and divide by 2 to the power of 8. Okay, then here we can, if you complete the calculation, this is the answer. Okay, and one thing that you can always remember, that the reference will always be larger than the V out. Okay, that's the main point, or things to always things that always to be remember. Okay, VR must be always then be output. So here we have a VR of the digital is equivalent to 10.0. Okay. Find the percentage of valve opening for 1 bit change. Okay, 1 bit means that what is okay. How much? Okay, how much? Okay, 1 bit change. Okay, you can start. You can take any value. Okay, any value of the input, and then you find the uh, output. Okay, let's see. Okay, we all know that the digital input will always start at 0 0 0 0 0 0, and then uh, the next value of digital input is n. Okay, n at 0. Sorry, at 0. The value, okay, 0 0 0 0 0 0 0 0. Okay, and at 0 0 0 0 0 0 0. Okay, but the next value will be 0 0 0 0 0 0 0 1. Okay, so we can use that one. Okay, what is dv out? Dv out when the next bit value, so 10.039 divided by 2 to the power of 8 multiplied with 1. You should get right. Okay, 10.039 divided by 256 multiply divide 10.0. So you get 0.039 volt. So basically, this is the resolution. The smallest change it can provide. Okay, to find the uh, so to find the percentage, okay, value. So just but the here what is the value here is 0. Okay, the next, okay, the next one bit change, this is the value. Okay, so you we can n1, okay, multiply minus n0 or divide by n0 times 100. So basically we get this answer. 1, 2, 3. Should be 1, 2, should be 3.9. Yeah, my answer is C, 3.9. But anyway, perhaps you can try at the other value, okay, with the smallest change, okay, and and then try to get the correct answer. Or perhaps this is the wrong answer, but anyway, okay. So that's the digital analog converter, and then analog digital conversion is the other side of the coin. So it basically convert analog into digital. Okay, so in this device, so you have your analog in, okay, and same need to have a VR, okay, and then the digital output. Okay, what's the digital output? The thing is that both you can use this same equation. It's just you need to know which one is in, which one is out. Okay. Okay. So this is the example of 8-bit. Meaning 8-bit means that it has 256 value, okay, from 0 to 255. Okay. In this example, okay, the reference is set at 1 volt. Okay, okay, so we have 255 or 256 values. Okay, and the smallest step, the digital step or our output is 190.5 millivolt. So resolution similar, like before. Resolution is the small value or conversion it can provide. Okay. Right. So for this example, you have an analog digital converter. But in this case, for analog digital, we refer to the voltage input. Okay, the range of the voltage input. Okay, for digital to analog, we use the resolution we use this formula. Okay, but in this one, okay, we are referring to the input scale, but still it can be considered. Okay, if you can use this if you know what is the reference. Okay, but in case where you don't know what is the input reference, okay, you use this formula. Okay, the range, the input range divide by the quantization level. Okay, quantization level. Okay, so in this case, the input range is from 0 to 10 volt. Okay, so input range means that the maximum value, maximum value minus the minimum value divide by the quantization level. Okay, so you can get the delta or V or the resolution. Okay, so in this case, it's not VR is not given. Okay, so in this case, the range input is 0 to 10 volt. Okay, so 10 minus 0 divided by concentration level, so the resolution of the analog to digital converter is 2.44 millivolt. In this example, you see the input, the analog input can swing from negative volt, the negative 10 volt to positive 10 volt. Okay, and whereas the resolution bit is 14 bit. Okay, so you use this equation to find the resolution. In this case, the resolution is 1.22 millivolt, much smaller than before. Okay, much smaller than before. So it is a better analog to digital converter. Okay, this one I think I don't want to explain in one by one. You can read in details. Okay, the different type of analog to digital converter, but in essence, the important thing is the resolution. Okay, the resolution, input range, and also the sampling rate. Okay, sampling rate. So those are the three important things that you need to know. Yeah, and this requirement is usually used when you want to choose a proper analog to digital converter. So given this one, this is just by the principle of the ADC, okay, the operating principle, and then the architecture or the how it was constructed, okay, using different design and also algorithm. Okay, but uh, what what is important, you need to know those three requirements. For example, okay, you need to know when you want to pick an analog to digital converter, you need to know your type of signal. If your signal is DC, okay, if your signal is DC, then the next thing is you have to think of the uh, maximum input. Okay, the maximum input or the reference value. Okay, what is the maximum you have to find? Okay, and then the next is the resolution. Okay, the sampling rate is not important for the analog DC signal because the signal is independent of frequency. But if your signal is uh, non-direct non-DC signal, meaning means that it has oscillation, okay, like sine wave, okay, and then it depends on frequency. So by principle, you need to choose or you need the sampling rate, okay, of the analog to digital converter must be at least twice the frequency of the signal that you want to convert. Okay, for example, your input analog signal is 60 volt. at least your analog to digital converter, the sampling rate, frequency must be 120 at least. Okay, otherwise you will not get any meaningful output. Okay, so you can read this what I explained about the importance of sampling rates. Okay, the importance of sampling rates. Okay, how it differ. Okay, how it is important for analog to digital converter. Okay, virtual. Now coming to virtual instrumentation. So this remind me about your assignment. So I will finalize the instruction for your assignment, and also I've already got the group members list. Okay, last time I asked in the group, and then we publish on the groups or at e-learning with the instruction, and of course, okay, the due date. Okay, I will fit into the amount of work should be done, uh, or should amount of work should be delivered uh, in your assignment. Okay, for your assignment. So virtual instrumentation basically uh, combinations or integration of software and hardware. Okay, where the user basically can use the tools, okay, as if it is an actual hardware. Okay, as if it is actual hardware. Okay, like popular virtual instrumentation like MATLAB, okay, Labview, so they can deliver virtual instrumentation. But like Labview, okay, later we'll explain. Okay. So the standard architecture of the virtual instrumentations of an actual instrument data acquisition, analysis, and the presentation or the user interface. Okay, so the data representation. So that is the basic requirement of an equipment. Okay, data sampling, and then some analysis requirement of some analysis, and then you show the result. Now, Labview is one of the most popular visual instrumentation tools. Okay, Labview. It is quite powerful, okay, for automation and okay, with automation or visual instrumentation. So I so it basically uh, the user can use instrument, okay, uh, from the option. It's like having an actual object, okay, in the software. Okay, you just select certain tools which represent by a block, okay, and then you can connect to a representation of physical input, like for example input button, okay, potentiometer, and then go it can be connected to like for example a comparator, okay, and then comparator connect to an LED, that you can perform like mm, logic input, okay, and then you check the output using the LED. So it is basically high level uh, not programming, high object oriented programming, Object-oriented means that the provider has already predefined or pre-designed the tools. Okay, so some disadvantages is that you don't have the privilege to change the object, uh, the function of the objects. Okay, but if you uh, so for like for people who don't bother about uh, the fundamental or the programming, so they can just pick the object and then they apply. So the good thing is that it is uh, in terms of the implementation is quite instant. Okay, quite instant. Rather than if you want, like for example, make a function and then you can use basic programming, like Labview in the platform Labview. So you do, but I think Labview also allows you to write your own function. Okay, they have the block or that you can pick and then you write your own function. Mean that you can define how the analysis is done or how the function behave, the function. Okay. Uh, so LabVIEW is much in terms of the automation is the most advanced in my opinion. LabVIEW as compared to other virtual instrumentation, Labview is the most advanced. So they provide also the hardware. So they are specialized in the automation, instrumentation and automation. Okay. Other software that can perform uh, similar trick or similar thing or which that can perform virtual instrumentation like MATLAB or Agilent VEE. But like MATLAB, the strength is not on. To in my opinion, the strength is not on the virtual instrumentation. MATLAB is more. The strength is much more on the analysis. The analysis, MATLAB, much powerful. Okay. Agilent, eh, Agilent, in my they much better in providing the hardware. But Labview both, okay, both way they are good in the virtual instrumentation and also the hardware they are quite advanced. Okay, but whatever platform or software that is being used, they all have to follow standards now standards. Like for example, if you they connect the hardware okay, to with the other hardware, the communication protocol must follow the standards. So that we will see in the next chapter lah. Okay. So with that, I conclude my class today, and inshallah we will continue our class next week. Thank you.